Okay, let's begin. Welcome back, everybody. So no surprise, a little thin today with the rain. So hopefully everybody's healthy, staying dry. They can't join us today. Okay, let me tell you about Bayesian forecasting. I'm just going to do this in the IID case. I'm going to allude to the non-IID case, like time series or something like that. Once we get into time series models, we'll cover it a little bit more, and I'll give you some examples there, but it really doesn't change anything. And I'll say what the change is today, the only change. So, Bayesian forecasting. So here's the idea. You see a collection of data, you observe, let me make that a little bit bigger. You get to see X's, some data. It comes from some model. And there's some unknown parameters in here. So here in the view of the kind of probabilistic statistical world, you see data, its randomness we describe through some function. If you see real data, you'll have to come up with this function. Make sure that it looks like your data, the parameters are interpretable for the questions you want to answer, so on and so forth. Sometimes we induce these models, or it describes kind of a process. Sometimes we're maybe using some asymptotics to come up with our models. So again, not a modeling class, but we get to see xi's from something. I'm going to say these are IID. And I'll distinguish the case where everything's not IID in a moment. And you want to know, so your goal, I'll say here's your question, what does the future look like? And so really you want to know X tilde, a future observation. Your question, really you want to just discern, given these xi's, what's this thing look like? And it's going to look kind of like what we see here. We want to describe not just what we think maybe our best guess is. So it'd be very tempting to say, well, maybe it's the mean. So, and in some distributions, it might be the mean. That might be your best guess. And that would be kind of interesting because the mean also maybe tells you about the mean parameter in the model. And so what we're really getting at is quantifying the uncertainty. So it's not always going to be the mean, it's going to be your best guess. It depends on what the model looks like. But you want to describe the uncertainty in this. And that's the whole name of the game in forecasting. And if you describe the uncertainty, what you should use, if you're ever going to use that to make some sort of prediction, is you should use all that information, the uncertainty. That's what makes you a statistician. Your goals as a statistician are to describe the uncertainty accurately. You'll be tempted through your collaborations to try to drag down that uncertainty. So what you should do is develop methods so that your uncertainty described in this observation, kind of matches what you see in the future. And so people like to make tight intervals. It's very tempting, and they'll go out of their way to come up with methods to give them tight intervals so that they can under-inform people about their uncertainty. But I think our job is always to quantify that uncertainty. That really is the goal. And people are a little bit fickle about predictions. People will say, I'm 95% sure that the future looks like this. Be prepared that 5% of the time, your answers don't look like that. That's what I would kind of like. So I'd kind of like something frequent test. But we can't always have that. We don't always do it. So I also want it to be conditional on what I've seen. Anyway, enough harping about that. How does Bayesian go about it? If you knew theta, and this could be multi-dimensional. So if you're a normal distribution, it might be the mean and the variance or something like that. If you knew theta, the best you can do in describing the uncertainty about x tilde about the future is through your sampling distribution. I'll say fx tilde given theta. And so if I knew theta, I would just describe my uncertainty through the sampling distribution. I'd plug theta in, boom. And then this function right here would model the uncertainty about my future draw. It's IID from everything else, so everything is conditionally independent. But keep in mind that conditional independent comes through theta. So this is equal to, if you knew theta, fx tilde given theta and x, where this right here is just my collection of data points, x1 to xn. So if I knew what theta was, it has nothing to do with the other x's because it's all conditionally independent. They don't tell you anything. And so no matter what you do in trying to forecast, you're gonna always have uncertainty just because the data you see has this random nature to it. Whether or not it's really random, maybe it's your measurement error that's inducing the randomness. Maybe it's actually random in nature, it's gonna flutter no matter what. But this randomness can come about for any number of reasons. We need to describe that. So in the IID case, your data doesn't help you to do the forecasting, except if you didn't know theta, then you can use your data to estimate theta. So in reality, you never know this. So if you knew this, but you never will. Sometimes, if you didn't know what f was, and of course you don't know f, what you would probably do is you'd place probability distributions on different f's. I'm not going to teach you how to do that yet, but later on when we get around to model selection, that is selecting the correct f distribution, you could place uncertainties on that and integrate over the model itself. Some people will call that Bayesian model averaging. And so a very good thing to do when you're trying to forecast is to average. Average over all the things you're uncertain about. So my fiction is that we know f, so we're not going to place a probability distribution on the function itself. You can imagine a Bayesian doing this. You place prior weights on it. Those prior weights probably have something to do with the data that they got to observe. We'll go into that later towards the end of class. So again, you always have some uncertainty. You're never going to be able to drive that down to 0. Okay, so you don't know theta. So what does a Bayesian do? I'll write it over here. So Bayesian forecasting always looks like this. And this is in the IID case. Again, I'll say something about it. It's always going to look like this. We're going to place a probability distribution on the thing we don't know. That's the future. And I'm going to condition on the stuff that I got to observe. I've seen it. It's empirical. So Bayesian just wants this. And once you convince yourself that's what you want, there's only one way to get it. So Bayes' rule, or Bayes in general, is kind of nice because after you have all your probability distributions and you formed them and you have good reasons for forming them, you just carry out your probability calculations. So we want to get rid of the parameter. We don't know it. So instead of just plugging in any old theta right here, you might be inclined to do something like this. I'm just going to take my best estimated theta and I'm going to plug it in. And the Bayesian says no, because you need to describe the uncertainty in that, in the average over it. So oftentimes Bayesian intervals tend to be a little bit wider than intervals where you just plug in theta, because you're going to have some uncertainty about that theta.
So you integrate over theta?
Say what?
So you integrate over theta?
So you integrate over theta.
That's right.
So we're going to integrate over theta with the posterior. So I'm going to take my original sampling distribution, plug in x tilde. If I knew theta, I would just have a point mass on it. I would be absolutely certain I'd be averaging over a point. But we don't know theta, so we come up with posterior distribution. And I just integrate over theta. So this is called the posterior predictive distribution.
So is f of x hat given theta, is that your model for x?
Yeah, that's this thing. So you get to know what this is. So this is that same x. So it's this function. So all you're doing in this calculation is you're integrating over your uncertainty in theta. And it's all very nice. So if all the x's are conditionally independent, you know how to form this right here. You just take the product over your sampling distribution, you plug in all your data points, and you now imagine it as a function over the parameters theta, the likelihood function. So the only thing that's going to change is your dependency in the data right here. So if things are not IID, you'd find the likelihood differently. And that's it. But you would also probably have some connection between this x tilde and some of the data, and you'd need to encode it right there. So you'd have to work with conditional independencies. Let's look at an example. I'll jump the gun for a second. Let's look at a non-IID example. Then later on, we'll come back around to it. So let's look at an IID example. And let's look at a non-IID example. Because instead of telling you things are virtually the same, I'll just show you. So let's say xi's come from a normal distribution. And these are IID. Okay. I'm going to let this be known for my example. If you didn't know it, you're going to integrate it out. It's going to change all of your normal stuff into t's. You saw that last time. Non-IID example. Let's do this. I'm going to say xi is distributed, that's a new word, is distributed normally, and it's going to depend on maybe the past last time. So I'm going to just write down theta, and it's going to have something to do with my previous observation. Sigma squared, and I'm going to let this be known. So this xi, the mean is mu, and it doesn't change. This xi depends on xi minus 1. This is called a Markov model. It depends only on the previous draw. Is it independent of all the other draws? No. It's conditioned through xi, but knowing xi minus, or it's conditioned through xi minus 1, but knowing xi minus 1 is sufficient for telling me what xi is. So now there's some dependency. This is an autoregressive 1 model. We'll come back and we'll study this a little bit later. Let's just write down what the likelihoods look like. So for this example, right here, our likelihood function is going to look like this. I goes from 1 to n. I'm going to have fxi, and it's going to be conditioned on mu in sigma squared. Okay, you can get rid of the sigma squared if you would like, because we know it. I'll just leave the notation there. And so in our case, this is going to look like this thing. I goes from 1 to n. I write down all of my sampling distribution. Sigma e to the minus 1/2 xi minus mu squared over sigma squared. This doesn't matter. We're just going to be writing down our likelihood function. And it looks, I usually, just to denote everything properly, I'll usually say what this is a function over. So that's kind of the notation we've been using in class. Sometimes I suppress the sigma squared, sometimes I don't. But if I were just creating a likelihood function over mu, I would take this equation and I'd treat mu as the variable. Not a random variable. It's not a probability distribution yet until I invoke Bayes' theorem. So that's our likelihood function. For this, maybe this is the unknown parameter. And so I'm going to put a constraint. Well, let's just leave theta as any old number. So we'll talk about issues with what the ranges of theta can be. But the likelihood function for this is going to look a little bit different. I'm going to go from I goes from I is equal to, and I need to talk about what data I got in all of this. So I'm going to say I goes from 1 to n. In this example, this one's a little bit different. I need the first x to kick this whole process off. So I'm going to say you know x0. If you didn't know x0, what might you do? You might put a prior on it. Some people take their first data point and they say, let's just condition on that. And so that's what a typical non-Bayesian person operating a Kalman filter might do. If you know what that is, great. If you don't, you're at no disadvantage right now. If you're a full-blown Bayesian, you might put a prior on your first data point. You might kick everything off from the next data point. So there's different ways to handle it. If you want to be the full-blown Bayesian, or if you want to be kind of a partial Bayesian in all of this. But again, we're just writing down the likelihood functions. So I'm just going to kick this thing off at I is equal to 1, so that when I have x0, I know what it is and I can plug it in. We'll deal with this at least very simply right now. Would I actually do that in practice? No. I would put a prior on x0. And basically, you're just averaging over your own circuit. And I'm going to say this is going to be xi, given beta xi minus 1 in sigma squared. So this would be my likelihood function for theta. This is going to be conditioned on all of my x's, maybe my x0 as well. I can denote that in sigma squared. So the likelihood function changes. What does this thing look like? I'll write it out. You'll get to play around with this, I think, on homework 4. So it's coming, but not yet. So this thing is going to be equal to, I could write it all out, 1 to n. This will look like 1 over square root 2 pi sigma. These are all normal distributions again. E to the minus 1/2 xi minus beta xi minus 1 over sigma squared. And I can get rid of this again. And if I knew what sigma was, I wouldn't need to plug that in right here. If I wanted to do full joint inference on sigma as well, I'd need to carry that with me. So the likelihood function changes. What changes over here when you do the integral? You'd have just dependency between this future point and the previous data point. And so you would just change this part to fx tilde given x, I would say beta xn sigma squared. So I take my last data point, condition on it, and then forecast the future. So in a non-IID model, you're still taking products of things. to build everything, but you have all the conditioning built into that model. How do you know what the right conditioning is? How do you build the right time series model? First thing you do is you take a time series class. But it's just like anything else that you do. You fit a model, you look at its residuals, you see where you're off, and you fix it. So it might not be autoregressive 1, maybe things depend on more previous data than you want to condition on that. How do you figure it out? The residuals have the story for you. Sometimes the errors are correlated as well. It's called a moving average model. And so you'll want to condition on that error structure as well. Those residuals might propagate. So take a time series class, they'll tell you how to do that. I'm going to go back to the Iip case. But really the only difference is writing down the likelihood correctly. You might have different reasons for coming up with your priors. Probably in this case, I'm going to place a flat prior on mu if I want to learn it. And just like in our old regression model, where usually we call these betas, this is autoregressive, I'm regressing on a previous thing, and this is just a regression coefficient. This is acting as a linear shift, so I'd probably place a flat prior on theta as well. Saying that, I might run into big trouble. So there's a lot to know about these sorts of models. That if theta is bigger than 1 or less than -1, this thing diverges. So it blows up. It's non-stationary. So you need to handle that differently. It depends on what theta is. Lots to be said about that. We're not going to say it now. Okay, any questions before I move on and I just kind of carry out Iip analyses? So pretty much everything that I'm saying in the Iip case is Bayesian forecasting in a nutshell. You'll just modify how you come up with your likelihoods. You'll put the right conditioning into your sampling distribution. So again, we're just looking at this. Ix tilde given x is going to be equal to fx tilde given theta, pi theta, given all of our data. The theta, integrate over all of theta. So posterior predictive distribution. And I love this, it makes sense to me. Just average away the things you don't know. Put a probability distribution on it, and now I don't have this isn't independent of the x's, it's conditionally independent through thetas. I don't know the thetas, so doing this averaging does create a dependency here. It's kind of cool. Okay. Examples. Let's do an example. This example is on your homework. I should probably mention homework number 2 is out. I didn't bring it with me. We can discuss it next time. This does appear. I do ask you to solve this integral explicitly and run through all the steps. I'll tell you the steps you need to run through. I'm not going to do all the algebra on board. So if you do want to see it, it is in a previous lecture. So from last year, I did show it. I came in after a review session. I wrote the integral on board. So if you do want to have a glance at it, but I'd like you to try more. I should be able to tell you enough today that makes you understand all these steps. So let's do xi's. They're coming from a normal model. Make this really easy so I don't have to integrate over sigma squared. I ask you to integrate over sigma squared on the inverse scale, so I ask you to integrate over the precision parameter and change everything. Everything will change to t distributions. So you'll carry out that analysis. You'll figure out an extra posterior or two. So let's just say this is known so that we can focus on the concept here. I goes from 1 to n, everything is Iip. Meaning if I knew mu and sigma squared, then all of my uncertainty is described through the sampling distribution. I know what my likelihood is. To do Bayesian analysis, I'm going to need a prior. So let's find pi x tilde, given all of my data, and I'll be explicit that you get to know sigma squared in all of this. So we want to find this thing. So if I want to do that and be a Bayesian, I need to come up with a prior on mu. So that's where I'm going to start. Somebody's told me this, or at least I've looked at the data. I look at a QQ plot, I do a distributional test, whatever I do, and I go, my data looks normal, I'm ready to proceed. Somebody's given me sigma squared, great. What a burden taken off of me, but I still need to do something with mu. So I need a prior. So step 2, I jump to immediately, and I come up with a prior. What would you pick?
Proportional to 1.
Some people say normal. So my next question is going to be which normal? Without any context, you have no good reason to come up with an answer to that. And so you might say, well, I'm going to take all my data, standardize it, and I'll just pick the unit normal. And it'll act like one data point. So maybe you do that. So I standardize all my data, I'll work with it on a standard scale, and I'll give my prior the weight of one data point, which would be a normal 0, 1. So maybe that's an answer. Maybe I don't want to standardize everything and do that. It still does place some tail beliefs on everything. So what would another good choice be?
Zero.
Say it again.
0 infinite.
0.
Infinite.
0 infinite. I see where you're going with this. But 0 infinite is not a distribution. Tell me about the shape. Huh? Flat. So we've had all these discussions. This is not a trick question. When I see this problem, I can argue flat prior on that, and I probably wouldn't go 0 to infinite. I'd go negative infinity to infinity, because presumably mu could be anything. So if I picked 0 to infinity and mu happened to be something that was highly negative, I will have just messed up the whole analysis. I'd be able to tell because my posterior would be slammed against the boundary. You know, we'd notice what induced that prior. So I'd probably be able to tell I had a bad prior choice. But I'd probably pick proportional to 1. The thing you need to do is explain it to somebody why you did it. And if you say it like this, nobody will like that. So you're supposed to say, it's the invariant to linear shifts. I don't want to put information about it. It's the conjugate limit. It turns out it is the optimal reference prior in a coverage sense. We're going to cover optimally. I'll give you your old interpretation about confidence intervals, but I'll also give you belief intervals out of it. So I would tell people the reasons, and I would explain that. And I would say it with some sort of authority. So if people had questions about it, I would entertain them. Jim? Step 1 was just to understand the model, I guess, and understand what the likelihood is. So step 1 is probably form the likelihood. Yes. Step 2 is a little bit of a jump without step 1, but step 1, understand the likelihood. Leanne, do you have a strong disagreement to any of these steps?
We don't discuss why it's more complicated.
I didn't say it's not good. I said you had to pick mu and sigma. You would have to pick your hyperparameters. So this one is the limit of the conjugate prior. That makes it obviates the need to come up with the hyperparameters. And so if you pick the conjugate prior, you might like it because you're like, I'll get an A on my math test. And I'll be able to write down the answer. But if you take this analysis into the real world, somebody's going to make you pick mu naught and sigma naught, your hyperparameters. You have to have good reasons for picking them. So I picked something where I didn't have to do that. That wasn't the only reason, because I could always use that. I don't have to pick hyperparameters. So it's a linear shift parameter, so understanding the likelihood would let me know that. It's the limit of conjugate priors. It also has some other optimality properties. This turns out to be the Jeffreys prior, the reference prior, and all kinds of other things I'm going to tell you about. So it's not that it's not good, it's that you won't be able to tell me what mu naught and sigma naught are. But again, this is much like the conjugate prior where sigma naught is extraordinarily large. And so large, I'm going to call it infinity. And it ends up resulting in this.
So we should define the parameter of the conjugate.
You can't come up with a posterior without picking those hyperparameters. They show up in the posterior, so that's not an answer until you pick them. So that's right. So on your math test, it looks really good, but as a statistician and providing an actual inference, it's incomplete.
How would you do that?
So it depends. So if you told me what the data was about, maybe I would go to my scientist and say, hey, what do you know about all this stuff? And so there is a form of subjective Bayes called elicitation. And it almost looks like a counseling session. So Tony O'Hagan came up with this over at Sheffield. I don't know how to do it. So it's like I would question you about quantile beliefs and what you know as a scientist. And there's apparently some art to doing it. I am not a good person to go to get somebody to elicit. So, but if you have domain expertise, if maybe you had an old study on things, and this is new data that came in a different form, and that study came up with belief intervals, they had 95% intervals, maybe I'd calibrate my normal to have those same intervals. So something like that. So it's hard, and that's where the art comes in. Since I don't really want to do that very often, I usually pick this. And then I have all kinds of mathematical reasons why I pick this. But good question. Don't know. Without the actual data and a real problem, I don't know. I think that's fair. Okay, so if you want to do the conjugate thing, go ahead. It'll work out almost exactly the same. So let's work through, well, you know, after saying all of that, let's go ahead and do it this way. So I kind of like it. Let's say that this is this, just so that we can not shortchange you on your algebra. So after that huge conversation about not doing that, let's do it anyway, just so we can work through a little bit more algebra. So conjugate. This is the whole question in Bayes. Which prior, why? So now we just need to work through our posterior predictive distribution. So our posterior predictive x tilde is just going to look like integral, again I'll write this down, fx tilde given mu. If you want me to condition on sigma squared or whatever, I guess I could. I'll write it in. And then I have my posterior distribution. It's going to be conditioned on all of my data. I could write in sigma squared in here that I know that. This also is going to depend on mu naught and sigma naught squared. I'll just write it in. I never really write this in. But since we're talking about it, let's just plug all that stuff in. Here are my hyperparameters. I'm going to integrate over mu. I'm going to do this between negative infinity and infinity. And so I'm just going to get rid of all my normalizing constants because I find them to be a hassle to carry around, but you could write them all down if you wanted to. And so this thing is going to look like integral e to the minus, oh, it should write proportional, So we're going to get rid of our normalizing constants, and we're going to do the same thing, and we're going to recognize the kernel. So e to the minus 1/2 x tilde minus mu squared over sigma squared. This one is going to be e, it's going to be subnormal as well. I'm working under the conjugate prior. It's going to be subnormal. And I need to recognize what those parameters are. This is going to be mu minus, and I'm just going to write down some notation for these. This is going to be my expectation on mu given x. I need to find what that is. This is going to be divided by my variance of mu given x. D mu. Do I need a variance term in here? Might have something to do with mu. Maybe it does, maybe it doesn't. Usually there's a square root, 2 pi, and then I'm going to put the square root of the variance of mu given x right here. This one is just 2 pi square root sigma. Do I need this term right there? When would I need it? How would you decide? If it depends on mu. Does this depend on mu?
No.
No. So it's a function of the data. It's telling you the uncertainty in mu. So we don't need that. So we have everything under proportionality. So I need to write down what this expectation invariants are, so I can complete this calculation. But this is the integral I want you to solve on your homework explicitly. Does anybody know what distribution this will be at the end of the day? So let's just ask a question before we chisel away at this. Question: what do you think? Pi x tilde given x is? It's normal. That's true. So I'm going to tell you a fact. So when I integrate something like this, we'll just write it down more generally. D theta. If this is normal, and this is normal, then this whole thing is normal. So if these two things are normal, then the whole thing will look like a Gaussian. So if this is a Gaussian function, that's a Gaussian function. When you integrate over them, it will still be Gaussian. How many times would I need to work through this integral to know that for the rest of my life? Exactly once. I'm going to ask you this question over and over and over again, and some of you will forget it periodically. You'll forget the shortcuts to working through this integral. So it would behoove you not to do that. Okay, this is going to be normal. We'll see that in a second. I'm just curious, what do you think the expectation is? We're after this, so we're going to try and convince ourselves this is normal. We're going to try to figure out its variance and expectation. I would have had a guess when I was a sophomore in college, because I knew what the predictive distribution was from my classical stats class. What do you think? Just some questions, just guesses. It's good to guess. You think this is centered at mu? I'm about to convulse. You don't know mu.
X bar.
Mu is being integrated across. This is the number 2 biggest pair that you can make in this class. Because when you integrate something, you work through it. It shouldn't have a mu in here because we've integrated across mu. So not mu. Dividing by matrices is the other big offender. Somebody will do this. We're going to get Stephen to not ever do this again. Any other guesses? X bar. It turns out you're right. Not quite. If I use the flat prior, it will be X bar. So if I take my hyperparameter variance, maybe X bar. Maybe that's a good answer. What do you think this would be if I used a flat prior?
Sigma squared. Or, yeah.
So somebody thinks maybe sigma squared. Sigma squared over n, we should be driving down variance. Anybody else? Getting closer. We're really close. Remember, this is going to be our uncertainty about mu. This is going to have to do with my uncertainty over here. But I still have additional uncertainty. So how certain am I about mu? Under the flat prior, this is my uncertainty. We've gone through that. Everything's centered around here. There's additional uncertainty in the forecast. So that's actually my uncertainty about mu, right there. How much uncertainty do I always have? Comes through sigma squared. It's going to be this. Sigma squared. This is my uncertainty about mu. And this is going to be my uncertainty that I'm always stuck with. So my sample uncertainty. And it turns out, if you were a non-Bayesian and you did things using a pivot in the traditional classical way, your answer would be normal X bar, and it would have this variance. We're going to derive that slightly differently. Okay. I'm going to tell you how to do this integral. So I need to work out what these are. So I need to find this posterior. Does anybody know what this is? We've done this in class. This was on your homework that you turned in yesterday, 2 days ago. Right? When stuff is new, this is hard. I'll remind you, X bar over sigma squared plus mu naught over sigma naught squared. 1 over sigma squared. Oops, this is divided by n. Plus 1 over sigma naught squared. That's inverted. What's the variance? I think we know. This is going to be 1 over sigma squared over n plus 1 over sigma naught squared inverse. Sum the precisions, inverted, it's the posterior variance. So we worked through these in class. This is a weighted average of X bar with whatever my hyperparameter is. The angle kill. So I can hear every bit of that. Okay. I do appreciate the enthusiasm. Okay, so that's that right there. So this is a difficult calculation to work through. And so what I need to do is I need to understand in terms of x tilde, what is this a distribution over? I need to factorize out the x tilde because I can't lose it. This is a distribution on x tilde. I need to retain this information right here, and that information, and I need to chisel away at this interval. I think because we have 4 minutes, I'm not going to do that. But let me do it the quick way for you. We'll see what this is. Let's just work under this real quickly and show you how to work through this very rapidly. But I do want you to get into the hang of being able to do this step by step. I can't do it in 4 minutes. So I do know what the answer is off the top of my head, though. So let's just do this, make everything easier. So I could convince myself real quickly that this is going to be Gaussian. How? I'm going to have an e to the minus x tilde squared term that I can factorize out of this. So I can expand the square and all of that, get my x tilde that doesn't depend on mu, factorize it out, and I'm going to have an e to the minus x tilde squared term in there that tells me instantaneously this is Gaussian. I would like you to complete the calculation. Once I know that, then the question is what is the posterior mean for that predictive distribution? What's the posterior variance? And I can do that very quickly. We'll come back next time and we'll talk about these rules. But we can convince ourselves x tilde given x is normal. If you can't convince yourself of that, you do more steps until you can. And so we just need to find expectation x tilde given x and the associated variance. Let me just tell you something. I can find this by using my iterated expectation formula. And maybe you guys know this, and maybe you don't. But this is going to be x tilde given mu. I'm going to write down everything I know. Sigma squared given x. And I'm going to condition on sigma squared and x over here. This might not look super familiar to you, but let me just show you. We'll come back to this integral later. This is true. Both of these things are true. Expectation of a random variable x is equal to expectation of x given y, expectation of that. Variance of a random variable x is equal to the variance of the expectation of x given y plus the expectation of the variance of x given y. If I know this, I don't have to do the full-blown integrals because I know how to work through the operators on everything. Question is what is y in that equation? It can be anything. Any y that has a random distribution, this is true in general. We can come back and prove this next time very quickly. It's a 1-second proof. And we'll start off with that. We won't prove this one, but the proof technique is the same, just a little bit longer. Who knows that this is true? Who does not? Okay, we'll go through it. This should come up in your probability class, but let's review it. What we're going to do when we work through all of this is we're going to apply this to the random thing that we don't know. This is acting as my y. I want to remind you in all of this, I'm conditioning on the stuff that I get to know. And this should always be conditioned. So really this is that. I want to just show you real quickly this inner expectation. We know what it is. What is this expectation? Expectation of x tilde given mu sigma squared and x. Expectation of x tilde given you get to know all of this.
What was the x bar over
It's not going to be X bar. Turns out you don't actually need to know what the data is in all of that. It's conditionally independent since it's IIP. And so the distribution of X tilde given you get to know mu is mu. That's the mean of that distribution. So this whole thing will be expectation of mu given X, and you get to know sigma squared. Under the flat prior, what's this? This was week 1 of class. It's X bar. This is the posterior mean. And so instead of going through all the hoopla with that integral, if I know my iterated forms, this is a 2-second calculation. If I don't know my iterated forms, it's a 15-minute calculation. So I think the punchline for today's class is go home, review your iterated forms, we'll use them. We're going to use them over and over and over again. If you know them on the midterm, problems are easy. If you don't know them on the midterm, problems are hard. So anyway, let's come back next time, go through this example. I'll teach you how to do that integral. And then we'll see some other things. Thanks, you guys.